When supplying power to a second building or structure from a main building that has a grounded electrical system, it is generally required to provide a separate grounding or bonding connection at the second building. This is to ensure electrical safety and to maintain a low impedance path for fault current to return to the source, which helps to trip over current protection devices like circuit breakers or fuses in the event of a ground fault. Here's why this is necessary and how it's typically accomplished. Firstly, the main reason for a separate grounding system at the second building is to prevent objectionable current from flowing on the grounding conductors between the two buildings. When a single grounding electrode system is used for both buildings and there are multiple paths for current to flow, some of the neutral current from the main building can return through the grounding conductor to the second building and back to the source. This can create voltage drops, cause nuisance tripping of ground fault circuit interrupters, and even pose a shock hazard. Secondly, the National Electrical Code (NEC) provides specific guidelines on how to properly ground separately derived systems in separate buildings or structures. The NEC addresses this situation in Article 250, which covers grounding and bonding requirements. The code mandates that a grounding electrode system be established at each building or structure that is supplied by a feeder or branch circuit, unless certain exceptions apply. Thirdly, to establish a separate grounding system at the second building, you must install a grounding electrode system. This typically consists of one or more of the following: 1. A ground rod, 2. A ground ring, 3. A metal underground water pipe, 4. A concrete encased electrode, often referred to as a UFA ground. The choice of grounding electrode depends on site conditions and local requirements. Fourthly, the grounding electrode system must be connected to the building's grounding system via a grounding electrode conductor. This conductor runs from the grounding electrode to the building's main grounding busbar or terminal. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the ungrounded conductors supplying the building. Fifthly, in addition to the grounding electrode conductor, a bonding jumper is required to connect the equipment grounding conductors of the circuit supplying the second building to the grounding electrode system. This bonding jumper ensures that all metallic parts of the electrical system are properly bonded together, providing a lower impedance path for fault current. Sixthly, it is important to note that the grounded conductor, typically the neutral, should only be connected to the grounding electrode system at one point. This is usually at the service entrance or the source of a separately derived system. Connecting the neutral to ground at multiple points can create parallel paths for neutral current, leading to the issues mentioned earlier. Seventhly, there are some exceptions to the requirement for a separate grounding system at the second building. According to NEC Section 250.32, if certain conditions are met, such as having only one branch circuit supplying the second building and meeting specific grounding requirements, a separate grounding electrode system may not be required. However, it is always best to consult the NEC and local electrical codes to ensure compliance. Eighthly, the size of the grounding and bonding conductors is crucial for ensuring effective grounding. NEC Table 250.102 provides guidance on sizing bonding jumpers, while Table 250.66 is used for grounding electrode conductors. These tables take into account the size of the service entrance conductors or the largest ungrounded conductor supplying the building. Ninthly, when installing a grounding electrode system, it is important to ensure that the electrodes are installed correctly. Ground rods should be driven into the ground to a sufficient depth to make good contact with the earth. Concrete encased electrodes should be encased in at least 2 inches of concrete. Metal underground water pipe should be in direct contact with the earth for at least 10 feet. Tenthly, regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be checked for corrosion and tightness, and grounding electrodes should be tested periodically to verify their resistance to ground. The resistance to ground should be low enough to allow fault current to flow easily back to the source. 11thly, in some cases, it may be necessary to install supplementary grounding electrodes to achieve the desired resistance to ground. This is particularly important in areas with poor soil conductivity. The NEC does not specify a maximum resistance value for grounding electrodes, but it is generally recommended to keep the resistance as low as possible, ideally below 25 ohms. 12thly, when working with electrical systems, it is always important to follow safe work practices and to use appropriate personal protective equipment, PPE. This includes wearing insulated gloves, safety glasses, and other protective gear as needed. Always de-energize circuits before working on them and verify that they are de-energized using a voltage tester. 13thly, another consideration is the use of surge protection devices, SPDs. SPD can help protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. SPD should be properly grounded to ensure that they can effectively divert surge current to ground. 14thly, when installing electrical systems in or around agricultural buildings, there are additional grounding requirements to consider. Agricultural buildings often have livestock present, which can be particularly sensitive to stray voltage. The NEC has specific requirements for grounding and bonding in agricultural buildings to minimize the risk of stray voltage. 15thly, healthcare facilities, grounding and bonding are even more critical due to the presence of sensitive medical equipment. The NEC has stringent requirements for grounding in healthcare facilities to ensure patient safety and to prevent electrical interference with medical devices. 16thly, when dealing with existing buildings, it is important to evaluate the existing grounding system and to upgrade it as needed to meet current code requirements. Older buildings may have grounding systems that are not adequate to handle the increased electrical loads of modern equipment. 17thly, when installing a generator or other separately derived system, it is important to follow the NEC requirements for grounding these systems. Separately derived systems must be grounded in accordance with Article 250 of the NEC. 18thly, the use of exothermic welding, also known as CAD welding, is often recommended for making grounding connections. Exothermic welding creates a permanent low-resistance connection that is less susceptible to corrosion than mechanical connections. 19thly, when running grounding conductors through metal enclosures, it is important to bond the conductors to the enclosure to maintain a continuous ground path. This can be accomplished by using bonding bushings or other approved bonding methods. 20thly, in areas with corrosive soil conditions, it may be necessary to use special grounding electrodes that are designed to resist corrosion. These electrodes are typically made of copper-clad steel or other corrosion-resistant materials. 21stly, when installing a grounding system, it is important to document the installation and to keep records of the grounding electrode locations, conductor sizes, and test results. This documentation can be helpful for future maintenance and troubleshooting. 22ndly, when working with electrical systems, it is always best to consult with a qualified electrician or electrical engineer to ensure that the work is done safely and in accordance with all applicable codes and regulations. 23rdly, the purpose of grounding is to provide a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly trip and clear the fault. This helps to prevent electrical shock, fire, and equipment damage. 24thly, bonding is the process of connecting together all metallic parts of the electrical system to create a common ground potential. This helps to prevent voltage differences between metallic parts, which can pose a shock hazard. 25thly, the equipment grounding conductor, EG, is the conductor that connects the non-current carrying metal parts of equipment to the grounding system. The EGC provides a path for fault current to return to the source. 26thly, the grounding electrode conductor, GEC, is the conductor that connects the grounding electrode to the grounding system. The GEC provides a path for fault current to ground. 27thly, the grounding electrode is a metallic object that is buried in the ground to provide a connection to the earth. The grounding electrode helps to stabilize the voltage of the electrical system and provides a path for fault current to ground. 28thly, the main bonding jumper, MBJ, is the conductor that connects the grounded conductor, neutral, to the equipment grounding conductor at the service entrance. The MBJ ensures that the neutral and ground are bonded together at the service entrance. 29thly, the system bonding jumper, SBJ, is the conductor that connects the grounded conductor, neutral, to the equipment grounding conductor at a separately derived system. The SBJ ensures that the neutral and ground are bonded together at the separately derived system. 30thly, when installing a grounding system, it is important to consider the effects of lightning. Lightning can cause severe voltage surges that can damage electrical equipment. A properly installed grounding system can help to protect against lightning strikes. 31stly, the NEC requires that all electrical equipment be listed and labeled by a recognized testing laboratory. This ensures that the equipment has been tested and found to be safe for its intended use. 32ndly, when working with electrical systems, it is important to follow all manufacturers' instructions and recommendations. This will help to ensure that the equipment is installed and operated safely and correctly. 33rdly, the NEC is updated every 3 years. It is important to stay up to date on the latest code requirements to ensure that your electrical installations are safe and compliant. 34thly, local electrical codes may have additional requirements beyond those specified in the NEC. It is important to check with your local electrical inspector to ensure that you are following all applicable codes and regulations. 35thly, electrical safety is a shared responsibility. Everyone who works with or around electrical systems should be aware of the hazards and take steps to protect themselves and others. Therefore, providing a separate grounding or bonding connection at the second building when supplied by a grounded system is crucial for ensuring electrical safety, preventing objectionable current flow, and complying with the NEC and local electrical codes.